Hello class. In this chapter, we will learn about the planar kinetic equation of motion. The first section of this chapter was a review of the mass moment of inertia, the I, computed at different locations. The reason why we needed it is because objects or rigid objects undergoing motion, whether it's translation or general motion or rotational motion, requires that Ig, which is equivalent to the mass. That Ig is a measure of the object resistance due to the translation, due to the rotation. Now, chapter 17, point 2 and point 217.3 we'll discuss the planar kinetic equation of motion, more particularly focusing on the translation, but we will introduce the equation of motion for general. So if we consider an object, and that object is located using a Cartesian coordinate system that does have an origin P, and the center of mass of that object is located at G, we know that from static, the weight of that object is represented at the G. Now, previously, we were able to understand how omega and alpha, which are the angular acceleration and angular velocity, are related. Now, in this section and forward toward the end of the semester, we're gonna introduce forces, 1 and forces 2 and forces any number, right? So this could be 1 and 2 until Fn, any number of forces, and also add to that moments, m1 and probably m2. These are free moments, 2 and could be m3, and all of them are vectors, right? All of them are vectors. This rigid body could have either a translation or a rotation or combined. When an object has a pure translation, let's say I have an object where all the forces Fn, F2, and also moments, could have moments, but these all together are causing this object to purely translate. Let's say it's translating, or translation means it's linearly moving. So the inertia at point G, or the center of mass, let's not forget the weight, or the kinetic equation or diagram, this is kinetic diagram, says that all the forces and moment causing this object to translate in X and also in Y, right? So summation of forces in X is equal to mass AGX, this is GX, and summation of forces in Y equal mass is AG in Y. This is AG in Y. So this is the translation acceleration of the center of mass in X direction, and this is the acceleration of the center of mass in the Y direction. we need another equation that describes that this system is not rotating. And that is, so this is equation number one. This is equation number two, to guarantee it's translating, but to guarantee that the system is not rotating, summation of all the moment measured at G must be equal to zero. Must be equal to zero. Now, these three equations are vector equations. Sometimes the calculation of moment about the center of the gravity might be cumbersome. So there is an alternative way to compute the moment about any point without violating that equation 3. Let's say I have a point over here. I'm going to call this point A. And let's say this system is translating about this line. So this is the translation. Definitely, if this is translating, then the moment to be the moment of all these forces and the moments, free moments about G computed must be equal to zero. Or you can say also that this is true if I calculate the moment of the inertia about any point within the system. Meaning, so if this is the sum AG as a vector, right? Then this inertia does have a moment, and that moment is, if I compute the moment of that inertia at the point A, that's going to be equal to the distance, this distance d, multiplied by that inertia. This is force multiplied by d, vertical distance measured from point A to the line of translation. That's going to give us a moment. So this is alternative. I will take an example to show what that means. When we say that there's no translation, we mean that the alpha, no translation, the angular acceleration alpha equal to 0. However, we might have omega. There might be omega, but must be constant, at least 0 or constant. We have a cart, and this cart is being pushed by 100 Newton with an angle given in a triangle shape, 3, 4, and 5. The total mass of this cart is 100 kilogram, and it's centered at G. The location of the center of mass, G, is given here. Now, if 100 Newton is applied, and if the wheel's mass is or are neglected, we want to find the normal reaction at each of the two wheels, A and B. Alright, now the procedures to follow is in fact simple. First, you have to establish a coordinate system, whether going to be an X and Y or an T, initial coordinate system. And then specify the center of the mass and give a sense of direction for the acceleration of the mass, AG. We draw the free body diagram and also the kinetic diagram showing all the external forces. We identify the unknowns, and then we apply the three equations of motion in the scalar format. Since we are already working on planar body motion, so it's easy to use scalar format. And then if there's a friction, don't forget to add friction opposite to the direction of motion. Let's go to step number 1. In step number 1, we chose our coordinate system x and y to be arbitrarily located somewhere here. And we label all the known and unknown forces. The known forces first coming from the external, it's 100 Newton in 3, 4, and 5 direction. We have the weight at the center of mass, G. We have reaction forces. They are different at A and B. This is not a particle, this is a rigid body. So we expect that depending on the location of the force and weight, the normal reaction will be different. So you might have more reaction or more stresses in the rear wheel than the front wheel, depends on the locations and magnitudes. So this is NA and NB are two unknown reactions. We want to, this is called the free body diagram. The kinetic diagram is when you show the direction of motion and the equivalent inertia. So the equivalent inertia here, we choose to have that the mass and is moving linearly, since it's not flying off the ground, so we don't have any acceleration on the y direction. So therefore, the only component we are interested in is summation of forces in the x direction, which is equal to mass multiplied AgX. So upon applying that and assuming x direction to be positive to the right, we sum all these components. Luckily, we only have one component, 100 Newton multiplied by the cosine angle, which is 4/5, is going to be equal to the mass by the linear acceleration measured at the center of gravity in the x direction, which is again is unknown. And that is, we can leave it as Ag because that's the only acceleration. And you solve that, you get the acceleration. Now, to find the normal reaction forces, we need to apply the moments. Now, the moments, you can apply it at the center G or any point, A, B, or anywhere. Since the geometry is given already, I can apply it at G. And let's not forget, if I apply the moment about G, then I will end up with one equation that shows NB and NB and NA, right? And we assume that counterclockwise is positive, clockwise is negative. So the cross product has to be also observed here. The other equation needed is summation of forces in Y. That's gonna give us NB plus NA minus 981 minus 100 multiplied by 3/5. This is the component in the negative Y. That's equal to 0, right? Because there's no acceleration in G. So two equations with two unknowns. So let's describe that in more details. And this is 0 because there's no translation in Y direction. NA positive plus NB negative 981. And that's the component from that one here. That's the first equation. Summation of moment about G, while you can do it at any point. But remember, because we do it at G, so the moment, summation moment about G equal to 0, excluding the inertia. Because it has a 0 position with respect to G. So that's equal to, let's break it down.
NA and multiply by, or it's a cross product, R cross NA, which is equal to the normal distance from here to here. This is from static, multiplied by NA, and that tends to rotate the object counterclockwise, which is positive here, so it's 0.6 multiplied by NA. Negative, now this is going to move it clockwise, so it's a negative, NB multiplied by the distance, measured from the G. Now, also the moment, we have two moments, or the 100 cause two moments. One is due to the component in X and the other to the Y. So the distance from here to here is already given to be 0.3 plus 0.4, so that's 0.7, and that's gonna help us calculate the moment of the 100 in the Y. The Y component is 3 over 4 or 3 over 5 multiplied by 100, and to get that moment you multiply it with the distance normal from here to here, which is 0.7, and it's counterclockwise, so you have it there, as well as the last component, which is the X component of the 100, which is 100 by 4 over 5, and that's tend to rotate the object clockwise, so that's why we have a negative multiplied by the distance from here to there, which is 1.2 minus the distance, the small distance, 0.5. So overall, you're gonna get 1.2 minus 0.5, 0.7, and this you get the second equation. Solve two equations, and then you get the result. So that's as simple as that. Now, the remainder of the equation or the examples are similar. In this example, we add a friction, and again assume the direction of the friction force is opposite to the motion. So I'm gonna just briefly show what's happening here. So a table has a mass, has a mass center at G, and a coefficient of static friction between the legs and the table. So this is the table here, is given by 0.2. We want to find the maximum acceleration of the truck possible without causing the table to move relative to the truck, and the corresponding normal reaction at legs A and B. Okay, now the most important part is to realize that we are looking at the maximum acceleration just before the objects start moving, right? So the maximum force at this instance is going to be 0.2 multiplied by the normal reaction forces, and that's normal, or the friction at each leg will be different depending on the normal force. So let's look at the free body diagram. This is the masses, and this is the two legs. Now, the frictional force that withhold this from not moving, right? We assume here to be a positive, and mu s multiplied by the reaction force at that leg, as well as for the leg A, right? So we assume both of them to be to the right, and this is a true assumption because this is not sliding. We're looking at the maximum, so it must be in the same direction. But if it starts to slide, then it's going to be opposite. But we're looking at the maximum just before sliding, then it's fair assumption to put that. If the sign of the FB and FA turns to be other way, then we later flip it. Okay, now upon applying the summation of forces in X for on the table, we have X direction is the positive to the right, and Y direction positive upward. We label all the forces and the reaction forces, including the friction and the weight. and the first force is going to be 0.2 NA. It's the first friction force. Second force is at leg A. That's equal to the inertia or the kinetic MAG X, which is the only one. So we are okay just leaving it AG. Similarly, for the y direction, we obtain. Now, the moment about G is equal to 0, and that is going to be equal to the moment of each force. Of course, the moment of the weight is 0 because it's coincide with the G. Okay. Now, the moment of NB and since we are given the geometry, 0.2 NA is the moment of the friction force, causing it to counterclockwise, so it's a positive. Also, the moment of NA and moment of the reactions. And so overall you get that equation by carefully applying the moment or calculating the moment about G for these four forces. Two equations with two unknown, and then you're able to find the reaction forces and then back substitute that value on the equation 1 to calculate AG, and then you get AG equal 1.96. So the maximum acceleration just before they start to slip is allowed to be 1.96 meter per second. Alright, so there are other examples. I would like you to take a look at them. Group problem solving, the presentation is already up. So you will learn more by practicing. Just remember how to apply the equation of motion, and on a safe side, always I would say use summation of moment at the center of G, and if you have to change the location, don't forget to add the inertia. Alright, with this we conclude the equation of motion translation. We have 3 more lectures, so remember that the final exam will be only on this chapter 17. Thanks.